In March of 1989, two respected electrochemists stepped in front of the world and announced something that, if true, could have changed civilization almost overnight. Martin Fleischmann and Stanley Pons claimed that they had observed evidence of nuclear fusion occurring inside a relatively simple laboratory apparatus at temperatures so low that the experiment could sit on an ordinary workbench. There was no miniature sun, no enormous magnetic reactor, no plasma heated to millions of degrees. Their setup involved palladium, heavy water, electricity, and an electrochemical cell. Yet they reported something extraordinary. More heat appeared to be leaving the system than conventional chemistry seemed capable of producing. If that excess energy really came from nuclear reactions, humanity might have stumbled onto an entirely new path to power. Fusion promised the dream scientists had pursued for decades: enormous energy from abundant fuel, without burning coal or oil, and without the same long-lived radioactive waste associated with conventional nuclear fission. Newspapers exploded with the story. Television networks treated it as a scientific revolution unfolding in real time. Governments paid attention. Energy companies paid attention. Laboratories across the world rushed to reproduce the effect. And then, almost as quickly as cold fusion appeared, the story began to collapse. Replication attempts failed. Scientists attacked the experimental methods. The physics community grew increasingly hostile. Within months, cold fusion had transformed from one of the most exciting scientific announcements of the century into a cautionary tale about premature claims. But beneath that familiar history lies a darker version of the story, one repeated for decades in books, interviews, alternative energy communities, and corners of the internet. That somewhere inside the chaos of 1989, researchers had discovered more than they were allowed to reveal, that crucial technical information disappeared, that experimental designs were restricted, buried, purchased, classified, or confiscated, and that the world came dangerously close to obtaining an energy technology powerful enough to destabilize entire industries. The popular version of this mystery sometimes describes it as a lost or confiscated cold fusion blueprint. But was there ever such a blueprint? Was anything actually taken? Or did a far more complicated collision between science, secrecy, money, reputation, and institutional power create a legend that survives because nobody has completely solved the underlying mystery? To understand why the events of 1989 became so explosive, you have to understand what fusion normally requires. The nuclei of atoms carry positive electrical charges, and positive charges repel each other. For two light atomic nuclei to fuse, they must somehow get close enough for the strong nuclear force to take over. Stars accomplish this through immense temperatures and pressures. Experimental fusion reactors on Earth attempt something similar by creating extraordinarily hot plasmas and confining them long enough for fusion reactions to occur. This is why controlled fusion has traditionally required giant machines, powerful magnets, lasers, complex engineering, and enormous budgets. Fleischmann and Pons were suggesting that nature might provide another route. Palladium has an unusual ability to absorb hydrogen. Under certain conditions, hydrogen isotopes can penetrate its crystal lattice in enormous concentrations. The researchers used deuterium, the heavier isotope of hydrogen, supplied through heavy water. Their controversial idea was that when enough deuterium entered the palladium lattice, conditions might somehow arise that allowed nuclear reactions at temperatures unimaginably lower than conventional fusion theory expected. Their primary evidence was calorimetric. Measurements suggested that the cells sometimes produced excess heat. They also investigated possible nuclear signatures that might accompany fusion. This was where the controversy became severe. If ordinary deuterium-deuterium fusion were generating enough nuclear reactions to explain substantial heat, conventional nuclear physics predicted corresponding quantities of neutrons, gamma radiation, tritium, helium, or other products. Yet the reported nuclear signals were inconsistent, weak, disputed, or apparently incompatible with the amount of heat being claimed. That contradiction became the central problem. The heat appeared to say that something extraordinary might be happening, while the expected nuclear products seemed to say that ordinary fusion could not be the explanation. To supporters, this suggested an unknown nuclear process. To critics, it suggested experimental error. And that distinction is essential because the mythology that followed often begins by pretending there were only two possibilities: revolutionary fusion or deliberate suppression. In reality, there was a third possibility, and mainstream science considered it the most likely one: extremely difficult calorimetry, combined with poorly understood electrochemical behavior, had produced measurements that looked revolutionary, but were not nuclear at all. The way the discovery was announced only intensified the crisis. Scientific revolutions normally move slowly through papers, peer review, replication, conferences, criticism, and independent verification. Cold fusion entered public consciousness through a press conference. Intellectual property concerns and competition between institutions helped accelerate the announcement before the scientific community had reached anything resembling consensus. Suddenly, laboratories everywhere were trying to reproduce an experiment whose critical conditions might not have been fully understood even by the original researchers. Palladium was not simply palladium. Its purity, manufacturing history, microstructure, loading behavior, surface chemistry, geometry, and treatment could potentially affect the experiment. Deuterium loading was difficult. Calorimetry required extraordinary care. Small systematic errors could become enormous when researchers were looking for relatively subtle excess heat inside an electrochemical system operating over long periods. Some laboratories announced positive indications, others saw nothing. Some reported neutrons, others failed to detect them. Some researchers became convinced that unusual effects existed but were unpredictable. Others concluded that the entire phenomenon was an artifact. Within weeks, cold fusion stopped being a single experiment and became dozens of different experiments performed under different conditions by researchers racing against headlines. Imagine trying to determine whether a machine works when hundreds of teams are building slightly different versions from incomplete instructions, while the entire world watches. Failure to replicate could mean the original claim was wrong, but supporters argued that failure could also mean researchers had not reproduced the exact microscopic conditions required inside the palladium. That argument created a scientific nightmare. A phenomenon that cannot be reliably reproduced becomes almost impossible to distinguish from noise. Yet, if the phenomenon depends on rare material conditions that nobody fully understands, inconsistent replication might be exactly what you would expect. This ambiguity created fertile ground for suspicion. When laboratories reported failures, believers said they had built the system incorrectly. When laboratories reported anomalies, critics said they had made measurement errors. Each side increasingly interpreted new evidence through a different framework. And somewhere inside this confusion, stories began circulating that the most successful cells contained proprietary details that were not being freely disclosed. The legend of the missing blueprint had found its first ingredient, an experiment whose apparent secret might not have been a single equation, but a collection of difficult manufacturing and operating conditions. Then came the institutional response. The United States Department of Energy assembled experts to evaluate the evidence. By late 1989, the prevailing scientific judgment was devastating for cold fusion. The evidence was considered insufficient to justify the extraordinary claims, and large-scale government funding was not recommended. Major scientific journals published criticism. Prestigious physicists publicly rejected the idea. Laboratories that had initially rushed into the field began leaving it. Careers and reputations became attached to positions on the controversy. For many scientists, the case was essentially closed. Extraordinary claims had been made before adequate verification. Independent groups had failed to reproduce the central results reliably, and the expected nuclear evidence did not support conventional fusion. But something interesting happened after the scientific establishment moved on. The experiments did not completely stop. A smaller community continued investigating what would eventually be described by terms such as low-energy nuclear reactions, or LENR. Researchers reported excess heat, helium, tritium, isotopic anomalies, transmutations, and other effects under various conditions. Many of these claims remained controversial, and reproducibility continued to be a major obstacle. Yet the persistence of anomalous reports kept the story alive. If cold fusion was simply a mistake, believers asked, why did researchers continue observing strange results? Critics had an answer. Because complex experiments generate anomalies, and without reliable replication, those anomalies cannot establish a new branch of nuclear physics. Supporters countered that history contains many examples of real effects that were initially difficult to reproduce because researchers did not understand the controlling variables. The debate therefore shifted. Instead of asking whether the original 1989 claim had been proven, the question became whether some unknown phenomenon might exist underneath the failed interpretation. This distinction is often lost in sensational accounts. Cold fusion as originally imagined, a straightforward tabletop method producing huge quantities of fusion energy, was never established. But investigations into anomalous nuclear effects in condensed matter continued. That surviving uncertainty became important because once mainstream funding and publication opportunities declined, researchers increasingly depended on private laboratories, military interest, industrial partnerships, patents, and proprietary methods. And when research moves from open academic science into environments involving intellectual property and national security, information naturally becomes harder to see. This is where the word confiscated enters the mythology, but it must be handled carefully. There is no universally documented historical event in which authorities walked into a laboratory in 1989, seized a complete working cold fusion reactor blueprint, and successfully erased the technology from civilization. That dramatic version makes a powerful title, but the available historical record does not establish it as fact. What did exist was intense competition over patents, experimental procedures, samples, laboratory records, funding, and ownership of potentially revolutionary intellectual property. The University of Utah and researchers involved in the discovery understood immediately that if cold fusion worked, its commercial value could be almost unimaginable. Patents surrounding the technology became extremely important. Meanwhile, government laboratories and military organizations had obvious reasons to investigate any technology claiming unprecedented energy density. None of this automatically implies suppression. Governments investigate strategically important technologies constantly. Companies protect intellectual property constantly. Universities fight over patents constantly. But from outside the institutions, legitimate secrecy and deliberate suppression can look remarkably similar. Suppose a researcher reports an extraordinary energy effect and then stops publishing technical details. Was the work disproven? Was funding terminated? Did a company acquire the intellectual property? Did patent attorneys instruct the researcher not to disclose information? Did a defense agency become interested? Did the researcher simply become embarrassed after failed replication? Without documentation, all of these possibilities can generate the same visible result: silence. Over time, silence becomes a blank space, and blank spaces attract stories. The blueprint may therefore be less a literal sheet of engineering drawings than a symbol for the missing knowledge people believed was necessary to make the effect reproducible. Perhaps it was a particular palladium preparation. Perhaps it was loading ratios. Perhaps it was surface treatment, current density, electrode geometry, impurities, temperature cycling, pressure, or some combination of variables. If one laboratory possessed a procedure that produced excess heat, while another did not, the difference between success and failure could look like a secret recipe. And in a technology potentially worth trillions of dollars, a secret recipe would be more valuable than almost any conventional blueprint. The economic implications explain why suppression theories became so powerful. Imagine for a moment that cold fusion had actually worked exactly as its strongest advocates hoped. A relatively compact device could potentially extract enormous quantities of energy from inexpensive fuel. The geopolitical consequences would be difficult to exaggerate. Nations dependent on imported fossil fuels could gain energy independence. Oil-producing economies could face profound disruption. Electricity generation could become decentralized. Transportation, desalination, industrial heat, synthetic fuels, agriculture, space exploration, and manufacturing could all change. Entire infrastructures built around extracting, transporting, refining, and selling conventional energy might lose value. This leads naturally to the question that fuels almost every suppressed energy narrative. Who would have something to lose? Oil companies, utilities, nuclear industries, governments dependent on energy taxes, and geopolitical powers built around resource control all appear to have obvious motives. But motive is not evidence. Industries frequently resist disruptive technologies, yet technological history also shows that enormous profits can be made by whoever commercializes disruption first. If cold fusion were demonstrably reproducible and economically scalable, suppressing it globally would require extraordinary coordination among competing countries, companies, scientists, investors, universities, and military establishments. A working device could be reproduced, measured, reverse-engineered, and eventually leaked. The stronger and simpler the technology, the harder permanent suppression would become. This is one of the strongest arguments against the grand conspiracy interpretation. But there is a subtler possibility. A technology does not need to be perfectly suppressed to disappear. It only needs to be unreliable enough that mainstream institutions consider it a bad investment. Funding dries up. Young scientists avoid the subject because it can damage their careers. Journals become skeptical. Investors see excessive risk. Research fragments into small private groups. Knowledge becomes proprietary. Replication becomes even more difficult because laboratories no longer exchange methods openly. Under those conditions, a potentially interesting but immature phenomenon could remain marginalized for decades without anyone needing to organize a conspiracy. Institutional incentives alone could create something that looks remarkably like suppression from the outside. And this is perhaps the most fascinating part of the cold fusion story, the boundary between scientific skepticism and scientific stigma. Skepticism is essential. Without it, science would drown in perpetual motion machines, miracle cures, impossible engines, and claims that collapse under controlled testing. Extraordinary evidence is not an insult, it is the price of extraordinary conclusions. Fleischmann and Pons were proposing something that appeared incompatible with established expectations about nuclear reactions. Demanding rigorous replication was completely appropriate, but stigma creates a different problem. Once a field becomes associated with failure or pseudoscience, legitimate researchers may avoid it regardless of the evidence. Funding committees become reluctant to approve experiments. Journals become reluctant to publish results. Universities become reluctant to hire scientists associated with the subject. This can produce a feedback loop. Weak research lowers the field's reputation, the damaged reputation reduces resources, fewer resources reduce experimental quality, and poor experimental quality further damages the reputation. Cold fusion became one of the clearest examples of this dynamic. Researchers who continued studying anomalous heat or nuclear effects often stopped using the phrase cold fusion entirely because the term had become toxic. Low-energy nuclear reactions sounded more neutral. Condensed matter nuclear science shifted the emphasis again. But changing terminology does not solve the central scientific challenge: reproducibility. If an unknown nuclear phenomenon exists, it must eventually produce reliable, independently verifiable measurements. A reactor that works once in 50 attempts cannot power civilization. A heat anomaly that depends on an unknown microscopic structure cannot become an industrial technology until engineers learn to manufacture that structure consistently. This is why the true lost blueprint, if one ever existed, would not merely explain why fusion was theoretically possible. It would explain how to make the phenomenon happen on demand. That recipe has never been publicly demonstrated in a form convincing enough to transform mainstream physics. And until that happens, the mystery remains suspended between two very different stories. One about a revolutionary discovery that was buried, and another about an experimental anomaly that people desperately wanted to become a revolution. Yet governments never completely lost interest in unusual nuclear phenomena. That fact is frequently presented online as evidence that authorities secretly knew cold fusion worked, but the reality is more nuanced. Military and intelligence organizations routinely investigate low-probability, high-impact technologies precisely because the cost of ignoring a genuine breakthrough could be enormous. If there were even a small possibility that condensed matter systems could produce useful nuclear energy, strategic institutions would have reason to investigate. The logic is simple. If your country dismisses the technology and another country discovers that it works, the consequences could be historic. Over the decades, researchers connected with government and defense institutions have continued examining aspects of low-energy nuclear reaction claims. Private companies have also repeatedly announced attempts to commercialize related technologies. Some generated enormous excitement before failing to provide convincing independent validation. Others disappeared quietly. Every cycle followed a familiar pattern: extraordinary announcement, tantalizing demonstration, promises of future verification, delays, arguments over proprietary information, and eventually disappointment or uncertainty. To believers, this pattern looked like interference. To skeptics, it looked like the predictable life cycle of a technology that never worked reliably in the first place. But notice how secrecy complicates evaluation. A company says it cannot reveal the internal reactor because of intellectual property. Investors say independent tests are coming. Researchers claim that exposing the device would allow competitors to copy it. Scientists respond that without access to the apparatus, the claims cannot be verified. Both positions make sense within their own systems. Commercial engineering depends on protecting secrets. Science depends on exposing methods. Cold fusion sits directly at the collision point between those cultures. The more valuable the alleged discovery becomes, the stronger the incentive to keep it secret. But the more secret it becomes, the weaker its scientific credibility becomes. This paradox may explain more of the cold fusion mystery than any confiscation story ever could. A truly revolutionary energy device would be extraordinarily valuable as proprietary technology, yet the very secrecy required to protect that value would prevent the open replication necessary to prove that the revolution was real. So what actually happened to the supposed blueprint from 1989? The safest answer is also the least cinematic. There is no solid evidence for a single, complete, proven cold fusion blueprint that was confiscated and hidden from humanity. There were experimental designs, laboratory notebooks, patent applications, proprietary methods, material samples, technical disputes, institutional conflicts, and enormous commercial expectations. There were also genuine scientific anomalies reported by researchers who believed deeply that they had observed something nuclear. Some continued pursuing those anomalies for the rest of their careers, but the leap from these facts to a successfully suppressed working reactor requires evidence that has never been publicly established. That does not mean every unanswered question has disappeared. Science is full of unresolved observations. Materials science, in particular, can produce behavior that changes dramatically with microscopic structure, impurities, defects, grain boundaries, and surface conditions. Palladium loaded with deuterium is a complicated physical system. Modern condensed matter physics has repeatedly shown that collective behavior inside materials can produce phenomena that would be difficult to predict by considering isolated particles alone. Superconductivity itself once appeared deeply mysterious. Quantum materials continue revealing unexpected effects. None of this proves cold fusion. It simply explains why declaring every anomaly impossible can be as intellectually careless as declaring every anomaly revolutionary. The correct scientific position is harder. Measure, replicate, criticize, improve, and remain willing to change conclusions. If someone tomorrow produced a sealed device generating sustained kilowatts of unexplained heat, allowed independent laboratories to test it, demonstrated appropriate nuclear products or a coherent alternative mechanism, and reproduced the performance repeatedly, the scientific world would not be able to ignore it for long. Nobel Prizes, investment capital, national laboratories and governments would converge on the discovery. Until such evidence exists, the strongest cold fusion claims remain unproven. And perhaps this is why the confiscated blueprint legend remains so compelling. It transforms an unresolved and frustrating scientific story into something psychologically satisfying. Instead of accepting that nature may have produced ambiguous signals that scientists still cannot control, the legend gives us a villain. Someone found the answer. Someone took it. Somewhere behind a locked door, the machine already works. But there is a final possibility worth considering, not because it has been proven, but because it reveals why the events of 1989 still matter. Perhaps what disappeared was never a machine. Perhaps it was a scientific opportunity. The announcement was rushed. The media turned a difficult electrochemical anomaly into an instant energy revolution. Laboratories raced to confirm it. Failures arrived faster than understanding. Reputations hardened. Institutions chose sides. Within months, a field that might normally have required years of careful materials research had become radioactive in the metaphorical sense. Maybe mainstream science was completely correct to reject the original claims. Maybe every major anomaly will eventually receive a conventional explanation, but imagine the alternative. Suppose there was a subtle physical effect hidden inside the noise, not the miraculous tabletop fusion reactor promised by headlines, but something genuinely new. If the backlash caused generations of researchers to avoid investigating it, then no secret agents were necessary, no documents had to be burned, no laboratory needed to be raided. The most effective form of suppression would have been cultural. Scientists would suppress themselves because the professional cost of touching the subject was too high. That possibility should not be used as evidence that cold fusion is real. It should be treated as a warning about how knowledge develops. Science requires skepticism, but it also requires curiosity. It needs mechanisms for rejecting false claims without making unusual questions permanently forbidden. More than 3 decades after Fleischmann and Pons stood before the cameras, controlled fusion remains one of humanity's greatest technological ambitions, while the strange world of low-energy nuclear reactions survives on the edges of mainstream research. There is still no universally accepted cold fusion reactor, no verified secret machine producing unlimited energy, and no documented confiscated blueprint capable of rewriting the global energy system. But the legend refuses to disappear because it asks a question larger than cold fusion itself. What happens when a discovery threatens existing scientific assumptions, enormous economic interests, and the reputations of the people evaluating it at the same time? Would we recognize a genuine revolution immediately? Would institutions protect it, reject it, purchase it, classify it, or simply fail to understand it? History tells us that revolutionary discoveries are sometimes resisted. It also tells us that extraordinary claims are often simply wrong. The uncomfortable truth is that while a revolution is happening, distinguishing those two possibilities can be incredibly difficult, and that is what makes March 1989 so haunting. For a brief moment, humanity believed that 2 scientists standing beside an electrochemical cell might have found a shortcut to the power of the stars. Then the door seemed to slam shut. Maybe there was nothing behind it. Maybe the measurements were misleading. Maybe researchers glimpsed a phenomenon they still do not fully understand. But if a reproducible cold fusion process is ever demonstrated in the future, historians will return to 1989 and examine every experiment, every notebook, every patent dispute, and every abandoned lead. And they will ask one extraordinary question. Did we discover the energy source of the future decades ago and fail to recognize what we were looking at?